Hello, everyone. Welcome to our last lecture of computer architecture. Today, we have another cutting-edge research in computer architecture. The first presenter is Ataberk Olgun. He's a PhD student in Safari Research Group, and he's going to present PiDRAM. Ataberk, feel free to start. Thank you.
Thanks, Mohammed. Oh, I hear myself. Maybe it's okay. Yeah. So I'll present PiDRAM, an FPGA-based framework for end-to-end evaluation of processing-in-DRAM techniques. I'll start with the executive summary. So we're motivated by commodity DRAM-based PIM techniques that can improve performance and system energy consumption without additional DRAM hardware cost. But there are challenges in integrating these PIM techniques into real systems. And existing infrastructure that is primarily used to evaluate these techniques cannot be used to efficiently study these integration challenges today. And our goal is to design and implement a flexible framework that can be used to solve system integration challenges and analyze trade-off of end-to-end implementations of these commodity DRAM-based PIM techniques. Our key idea is to develop PiDRAM. Is an FPGA-based framework that enables system integration studies and end-to-end evaluations of these techniques. And we evaluate PiDRAM with two PIM techniques on a FPGA prototype. In our first case study, the first PIM technique we evaluate is RowHammer. It allows in-DRAM bulk data copy operations, and it provides 119x speed up compared to a CPU-only copy operation throughput. And it only takes 198 lines of Verilog to implement and 565 lines of C++ code over PiDRAM's flexible code base. In our second case study, we study a DRAM-based random number generation technique, and we show that we can generate 8.3 megabits per second random numbers with only 220 nanoseconds latency. And it took us 190 lines of Verilog and 78 lines of C++ code to implement over PiDRAM's code base. So this is the outline of my talk. I'll start with a brief background on DRAM. Today, DRAM systems are organized as such. We have a CPU, and inside the CPU, we have a memory controller. The memory controller interfaces with a DRAM module that contains multiple DRAM chips over a DDR interface. And inside each chip, we have multiple banks that share the same interface. And inside the bank, we have multiple DRAM subarrays. And inside the subarrays, we have word line drivers and sense amplifiers. DRAM mats are placed in between the word line drivers. And inside each mat, we have DRAM cells laid out as a two-dimensional array of rows and columns. And finally, we have a DRAM cell that is connected to a word line through an access transistor and the bit line. This DRAM cell has two main components, the capacitor and the access transistor. The capacitor stores charge, and the access transistor determines if the cell is being accessed. The access transistor is enabled by the word line. And when the word line is enabled, it connects the cell's capacitor to the bit line. And there's also a bit line bar signal, which is the inverse of the bit line signal connected to the sense amplifier, which reads out the value in the cell. And that happens when we enable the sense amplifier using this enable input. So we'll look at how we access the cell. Initially, we have the bit line voltage set to VDD over 2, and the capacitor is fully charged, so it encodes a value of 1. So first we will enable the word line, and this will connect the capacitor to the bit line. And once this happens, the capacitor loses charge. In this case, it shares its charge with the bit line. So the bit line voltage deviates slightly towards VDD. And when we enable the sense amplifier will amplify this deviation up to VDD. So this operation also restores the charge lost in the capacitor back to the capacitor. And we will look at the DRAM operation at the granularity of a subarray here. The granularity of cache lines here, because we typically access cache block-sized regions in DRAM when we send read commands. So this bottom on the bottom, we show the command sequences that we will execute to access DRAM cells. So first, we need to activate a DRAM row. And for that, we send an activate command. This will enable the word lines in that row and copy essentially all the cells to the sense amplifiers. Once this values are in the sense amplifiers, we can send read commands to read data in cache block granularity from the sense amplifier. If we want to access a different DRAM row, we must first pre-charge the bank and then activate that row, and then we can do the same thing. We can read data in cache block granularity again from the sense amplifiers. Yeah, I'll talk about two important timing parameters. First one is called TRAS. This is also called the activation latency, and it determines the time between successive activate and pre-charge commands to the same DRAM bank. And we must wait at least for TRAS amount of time before we send a pre-charge command after sending an activate command. And the second parameter is called TRP. It's the pre-charge latency, and it's the time between successive pre-charge and activate commands to the same bank. And then the final timing parameter is called TRCD. And TRCD determines the minimum amount of time between the activate command and the first read command we send to that activated DRAM row. I'll introduce one commodity DRAM-based PIM technique. That is, so first I will introduce PIM techniques in general. The commodity-based DRAM-based PIM techniques, they use the operational principles of commodity DRAM chips to perform either bulk data movement or computation in memory. And I'll give two relevant examples to this. The first one is the in-DRAM copy operations. We can copy data at row granularity from one row to another in DRAM by using these operations. And the second example is DRange, which is an in-DRAM true random number generation technique by using access latency failures. I'll talk about the first one in more detail. So this is the key idea of in-DRAM copy operations, and it was initially presented in RowClone, a paper presented in Micro 2013. So here we see a diagram of a DRAM subarray, and we have the source row and the destination row in different colors. We want to copy the source row to the destination row. So what we're going to do is we're going to first activate the source row, and that will copy the source row data to the row buffer. And then we want to somehow take the data back to a different row. So the first step is already implemented in commodity DRAM chips. This is just an activate command. This is what an activate command does. And RowClone presents a minimal circuitry design that allows us to do the second part of this operation. And I'll talk about that in more detail. Now I will introduce PiDRAM. So just to reiterate on our goal, we want to develop a flexible framework that can be used to solve system integration challenges and analyze the trade-offs of these commodity DRAM-based techniques. Therefore, we identify the key components that are shared across PIM techniques, the implementations of PIM techniques. And we implement these key components in a customizable way to provide modularity and enhance the extensibility of our framework. And essentially, we provide a common basis to enable support for PIM techniques in PiDRAM. So I'll describe the four key hardware and software components we implement in PiDRAM. So the first one is a flexible PIM operations controller and an easy to extend memory controller. These are two hardware components we identified. And on the software side, we have an extensible software library that can be used by programmers to perform these operations, and a custom supervisor software that implements the key OS primitives that users need to use to implement new PIM techniques. I'll talk about these in more detail. These key components are attached to our real computing system. So we provide the PIM operations controller and PiDRAM memory controller in the hardware system. The custom supervisor software runs on the hardware system, And finally, the extensible software library is used by the supervisor software to perform these operations. I'll describe each component over this diagram. So the first is the PiDRAM operations controller, PIM operations controller. It decodes and executes PiDRAM instructions. For example, for an in-DRAM copy operation, we implement a new instruction that's a PiDRAM instruction. And it receives these instructions over a memory mapped interface. And this makes it portable to other systems with different CPU ISAs. This is essentially an ISA transparent way to implement the communication between the host system and the operations controller. And the simple interface, it's connected to the memory controller over a simple interface, where the protocol used in this interface is the PiDRAM memory controller sends a request to perform an in-DRAM operation and waits until completion and then reads the results. The second component is called PiDRAM memory controller. It performs processing in memory operations primarily by violating DRAM timing parameters. And it supports the command scheduler in the memory controller supports conventional memory operations like loads and stores. And it implements one state machine essentially to perform each of these operations, including the processing in memory operations. And this allows users to easily replicate these state machines to support a new operation in their PiDRAM prototype. And the physical interface in the memory controller controls the physical DDR3 interface, meaning that it receives commands from the command scheduler and operates the physical DDR3 pins, essentially. On the software side, the PIM operations library contains customizable functions that interface with the PIM operations controller. And it provides the software interface for performing these operations to the user via the custom supervisor software. So to do so, it executes load and store requests and it communicates with the PIM operations controller here. And finally, the custom supervisor software exposes these operations to the users, and it also implements the necessary operating system primitives to allow implementation of new processing in DRAM techniques. And for example, the memory management subsystem. Now I will describe an operation execution flow, PIM operation execution flow over this diagram again. So we will execute a copy function. The user will call a copy function to perform a row clone copy operation. So first, the user application will make a system call with the following semantics. So it wants to copy from array A to array B n contiguous bytes in virtual memory. The second step, custom supervisor software calls the copy function of the extensible library. And this has the following semantics. So it has a source DRAM row and the destination DRAM row. And the translation from the virtual addresses here to source and destination DRAM rows are made by the custom supervisor software. This, in turn, will cause the PIMolib, or PIM operations library, to perform two store instructions in the CPU. The first instruction will set the instruction register in the PIM operations controller, and that essentially holds the information that we want to perform a copy operation from source DRAM row to destination DRAM row. And the second store sets the start flag in this flag register in the PIM operations controller. And this will essentially start executing this operation. Now, the PIM operations controller will tell the memory controller to perform a row clone operation. And at that point, it will reset the start flag to 0, and it will set the acknowledge flag so that the software is aware that this execution has started. And the PiDRAM memory controller then will issue commands with violated timings to the DDR3 module to perform the row clone operation. When it's done, it will set the finish flag, and basically the library periodically checks either the acknowledge or the finished flags based on a user-defined parameter using load instructions to understand basically when the operation finishes. And the copy call, function call will return when this periodically checked flag is set. And we didn't use the data register in this example. It's not used for row clone operations because the data, the result is, it resides in memory after the operation. So we copy the source row to the destination row. The result is in the destination row. But we use it for to store random numbers generated by D-range operations in our prototype. Okay, so to summarize these components, we have 4 key components that are highlighted here. Together they orchestrate the PIM operation execution, and these components provide the key extensible basis basically for end-to-end integration of PIM techniques. And we develop PiDRAM's prototype. The system that I described is implemented in this FPGA along with a RISC-V system. And we use the Xilinx DC706 FPGA board for this prototype. And in the RISC-V system, we use the Rocket core. It's an in-order pipeline RISC-V Rocket core with L1 data caches, and L1 caches and a TLB. And we use a 1 GB DDR3 Micron module, and you can see the module number here. I'll continue with the case studies if there are no questions anywhere. No. Not on Zoom, okay. Do you have, no. Okay. Yeah. So we conduct 2 case studies in PiDRAM. The first one is in DRAM bulk data copy operations, or row clone. And the second one is in DRAM true random number generation, which is also what's been proposed by D-Range. And the purpose of these case studies is to essentially demonstrate the flexibility and ease of use of PiDRAM. And I will talk about this case study, the first case study, row clone, in today's talk. So the key idea of our case study of how we perform these operations is to use carefully crafted DRAM sequences. And we use the sequences that were demonstrated to perform row clone operations by a prior work in real DDR3 chips in our work. And these sequences essentially are activate, pre-charge, activate command sequences with greatly reduced TRAS and TRP timing parameters. So here I will describe this operation over a diagram. We have a DRAM subarray. Inside of the subarray, we have a source and a destination row. And we want to copy source row to the destination row. We first activate the source row. We then wait for 10 nanoseconds. So this is much smaller than the default 32 nanosecond TRAS timing parameter. And then we send a pre-charge command. And then we wait for another 10 nanoseconds. And this is smaller than the default TRP timing parameter of 17 nanoseconds. So in doing so, we can copy the source row to the destination row. To implement this in PiDRAM, we first extend the memory controller to support this DRAM command sequence. We add a new state machine, essentially, in the command scheduler. And we expose this operation to PIMolib by implementing the copy instruction. Together, these take only 200 lines of Verilog code to implement over PiDRAM's code base. There are 2 challenges in integrating row clone to an end-to-end system, end-to-end in a real system. The first one is related to memory. It's memory allocation constraints that stems from the intra-subarray operation, essentially. And the second key challenge is memory coherency. And this again stems from the fact that we're doing computation in DRAM. So we're operating possibly on stale data. If we have cached copies of a certain piece of data that we want to copy, we have to first invalidate those cached copies before we perform the operation. And to do that, we implement the CL flush instruction in the RISC-V CPU. And what it does is it evicts a cache block given an address back to the DRAM module. And I'll describe the first challenge in more detail now. So row clone has some memory allocation requirements, and I'll show them over this figure. The first one is what we call the granularity constraint. granularity requirement. It says that the operands must occupy DRAM rows fully. In the first example, if we copy source 1 to target 1, we would be overwriting this data here, the remaining data in target 1's row, with the remaining data in the source 1's row, even though we didn't intend to do it with the operation. So this is not good. The second constraint is called alignment constraint, and it says that the operands must be placed at the same offset. If we perform a row clone operation from source 2 to target 2 in the second example, we essentially cannot do it because of how the DRAM bit lines are organized. So source 2 needs to reside, source 2's bits must reside in the same bit lines as the target 2's bits. And the third constraint we call the mapping constraint, and it states that we must place the operands in the same subarray, place the operands that we want to copy in the same subarray. And this is because we can only perform row clone operations within a single subarray. And in this example, the fourth allocation of source and target rows satisfies all three requirements, and we can perform a row clone operation from source 4 to target 4. Okay. And to overcome these challenges, we implement a new memory allocation function in the RISC-V system we developed. So our goal is to allow the programmers to allocate virtual memory pages that are mapped to the same DRAM subarray and aligned with each other so that we can perform row clone operations between them. And the key mechanism of our allocation mechanism is essentially to distribute the virtual pages to different banks to still allow us to exploit bank level parallelism in DRAM. And while mapping them, these virtual pages to DRAM rows in the same subarray. Essentially, we expose this mechanism, this allocation mechanism, using this alloc align call. It takes two parameters. The first one is size, and the second one is called ID. Size is the number of bytes we want allocated, and ID is used by the allocation mechanism to put different allocations into the same subarray. So if you have arrays A and B allocated using different alloc align calls, if they use the same ID, they will be put in the same subarray. So we can copy data from one to another. And you can check our paper for more details. I'm not gonna dive into this given the interest of time. And now I'll talk about how we evaluate PiDRAM. This table shows our system configuration. We use two micro benchmarks. One's called CPU copy, the other called row clone copy. The CPU copy micro benchmark uses CPU load store instructions, whereas the row clone copy benchmark uses the in-DRAM copy operations to copy large arrays. And we evaluate one copy and one initialization heavy workload. Compile workload is initialization heavy, whereas the fork bench is copy operations heavy. And we also evaluate one workload from spec 2006, libquantum, where we replace calls to the call log function, which zero initializes a large array with in-DRAM initialization operations. So this plot shows the throughput improvement for row clone copy and initialization operations over CPU copy and initialization operations for different array sizes. And the conclusion here is basically that in-DRAM copy and initialization can improve throughput by 119x and 89x. Here we show the overhead associated with the CL flush operations. One detail I missed is here we assume that the data is up to date in memory. So we don't have to flush any cached copies of the data that we are copying or initializing. Here we assume a certain proportion of the data we operate on is dirty, meaning that we have to evict them from caches. And even for the cache blocks or the proportion of data that's not dirty, we still execute a CL flush operation to make sure that the copy of the data is not, there's no copied cache copies of the data. So the x-axis shows the proportion of these blocks of this data, and the y-axis still shows the throughput improvement for copy and initialize for DRAM copy operations over CPU copy operations. And we see that CL flush operations dramatically reduce the potential throughput improvement provided by row clone copy and initialization. We evaluate other workloads. This plot shows the speed up gained when we use row clone copy operations. For the fork bench workload, for different configurations of the fork micro benchmark, on the left y-axis we show the row clone speed up, and on the right y-axis we show the time spent on mem copy operations for the fork bench workload. And we see that as the number of pages copied by the fork bench workload increases, the performance improvement provided by row clone also increases, because the mem copy operations start taking a greater fraction of this benchmark's time. And row clone copy operations significantly reduce the time spent on copying data. And for the compile workload, the initialization heavy workload, we observe 9% execution time reduction when we use in-DRAM initialization using row clone operations. And this is only 9% because the compile workload spends only 17% of its execution time in initializing the data that it operates on. And finally, for spec-lib quantum workload, we observe a 1.3% end-to-end execution time reduction, and this is 1.3% only because libquantum only spends 2.3% of its time on initializing data, and row clone initialization greatly improves the execution time for that portion, essentially. Okay, I'll conclude. Are there any questions? No, okay. Okay, yeah, so here we were motivated by DRAM, commodity DRAM-based PIM techniques that can improve system performance and energy efficiency greatly without incurring additional DRAM hardware cost. And the problem is, using existing infrastructure, we cannot evaluate them. And therefore, we develop a new flexible framework that can be used to evaluate these techniques. And we developed an FPGA-based framework called PiDRAM. And it allows evaluation of commodity DRAM-based PIM techniques using real unmodified DRAM chips. And we evaluated using 2 commodity DRAM-based PIM techniques on an FPGA prototype. And we show that row clone operations can improve system performance in a end-to-end evaluation or end-to-end implementations of row clone can improve speedups greatly, system performance greatly, and DRange can generate random numbers at high throughputs and with low latency. Okay, I think, yes. PiDRAM is also open sourced on GitHub, so you can access PiDRAM using this link and make your modifications or use it in your next project. And we have an extended version of our paper on archive on this link. And I have a longer talk and a tutorial on how you can use PiDRAM on YouTube on this link that you can watch if you're interested. Thank you for your attention.
I have a question.
Yes.
You said in the beginning of the talk that you will only talk about one case study today.
Yes.
In the interest of time. So when we will be able to hear about the other case studies?
The other case studies, well, do I have time?
Yes, sure.
Okay. So the other case study we evaluate is DRange. I might have some slides on it. I should have some slides on it. Maybe I can go there and next slide. Yes. The key idea of D-range is that there is a variation in error distribution when we access DRAM cells with a reduced TRCD timing parameter. So there are cells that are very likely to fail when you access them with a reduced TRCD, and there are cells that have very low chance of failure when you access them with reduced TRCD. And it makes the key observation that there are some cells that fail with 50% chance, so essentially randomly fail when you access them with reduced TRCD. And it proposes using these cells to generate random numbers. The basic idea is to access the cell with a reduced timing parameter and use it as a random bit. So to do that, we implement this in PiDRAM, and we identify DRAM cells that fail randomly, these cells, when accessed with a reduced TRCD parameter. And we identify 4 cells in a DRAM cache block that have this characteristic. And we use that cell to generate those cells to generate these random bit streams. So we repeatedly access them with reduced TRCD, we generate bit streams. And we implement a random number generator controller essentially inside PiDRAM's PIM operations controller that periodically performs these operations and puts them in a buffer, puts the generated random numbers in a buffer. And that buffer is 1 kilobyte large in our implementation, and programmers can read these random numbers using the rand-DRAM function call implemented in the PIM operations library. And this took 190 lines of Verilog code and 74 lines of C++ code to implement on top of PiDRAM. And we evaluate it by using a micro benchmark that reads random numbers essentially. It just calls the rand-DRAM function. And this plot shows the TRNG throughput we observe on the y-axis to changing TRNG period. What TRNG period means is the time it takes the random number generation controller to execute one random number generation operation that retrieves 4 random bits from DRAM. So if it's we can go down to 220 in our implementation. And when we have 220 nanosecond period, we can generate 2 random numbers at this throughput. Here, it's 8.3 megabits per second. And that is the second case study that I didn't talk about. Yeah.
Okay, so are there 2 case studies in the paper?
There are 2 case studies.
Okay, so what if I want to extend and with Quark, for example, over there?
Yeah.
I remember that it's another random number generation paper, right?
Yes.
What kind of effort would it take? And in combination to that, I want to ask another question actually.
Yeah.
If I understand the current version of PiDRAM only supports zinc boards.
Mm-hmm.
So let's say I want to port it to some more advanced boards, some, I don't know, let's say Alveo board with ultrascale, or some like HBM supported boards. And I want to rent or book, whatever term is used for that,
yes,
in Amazon servers and just deploy this and run my benchmarks on it. So what kind of effort would it take for me to, for a random engineer, let's say, to do that?
The answer is it depends. No, there are 2 questions here. Thanks for the good questions. The first one is, what does it take to implement a new in-DRAM computation technique? Basically, we talk about new things that can be implemented in the paper in this table, but we describe here their challenges, integration challenges. And as for what needs to change, for example, let's say that you wanted to implement Ambit, which is performing bitwise operations in DRAM, which is possible to an extent in real DRAM chips today. And to do that, you need to send a new command sequence with violated timing parameters. So you would implement a new state machine in the PIM operations controller, the PiDRAM memory controller here. You will implement a new new state machine here that will execute a new sequence of commands. And then you would expose it to the rest of the system by changing the instruction encoding here. And finally, you need to implement some function calls that essentially just store the correct instruction. Let's say the ambit instruction here. So doing that would probably take nothing more than 198 lines of Verilog code, because now the row clone use case we have already provides some of the common requirements that the ambit study will have. I don't know how many hours of effort it would take, but if you're familiar with FPGA design and maybe a bit with RISC-V, maybe 2 or 3 days. And the other question is, oh, do you have something to add to this? Or?
No.
Okay. The other question is if you can port PiDRAM, essentially make PiDRAM prototypes available on newer boards or more powerful boards, different boards than Zinc FPGA boards. Yeah, that is a bit trickier, I would say, than implementing a new use case and evaluating it on this board or 2 other boards that are that have Zinc systems in them. The main reason is because the RISC-V system we're using along with PiDRAM's components kind of depends on this platform, this Zinc platform, to work out of the box. So 2 options, I think, is either to port this whole RISC-V system to a new board, or to take PiDRAM's components and put them in a system that you already have running in those new boards. So the second option would take less time, but you would be using some other, maybe perhaps it's still a RISC-V system, but it's not going to be the exact same system. But you would be able to control your changes more, and that will take less time for you to implement. The other option is to port this whole system, essentially this system, to a new board. And that would require more invasive changes. That could take weeks or months, depending on the workforce you have.
So in this figure, for example, can we think of like this PIM operations controller as an accelerator module, let's say, and the Rocket chip and RISC-V parts, let's say we replace them with some other cores that are already implemented in some FPGAs, like some ARM cores, for example. Exactly. So it also works that way, right?
Yeah, sure. I mean, that's the first case I tried to describe. So you take these out, and obviously the software components also, and you put them in the new system, a new FPGA prototype system, where you have some other CPU supported, or where you have your own CPU already supported. Any CPU already supported. But yeah, I mean, you can easily plug these out and plug them into your new system, because one reason why we have this memory mapped communication here is it allows you to plug this in your system's memory bus, and your CPU just needs to execute some stored and load instructions to communicate with the PiDRAM operations controller, which is, in one sense, it's like an accelerator, yes.
Okay, I don't have any more questions, thanks.
Thanks.
Thanks a lot, Ataberk.
Thanks.
Are there any more questions? Okay. So the next talk is about pLUTo.
Thank you. Thank you.
Thanks a lot. So the next talk is for pLUTo. Geraldo is going to lead discussion about that. Geraldo is a PhD student in software research group as well. Geraldo, please feel free to start.
Hello, everyone. Welcome to another talk on processing memory. Hopefully, this is interesting for you. So today, I'm not João, I'm Geraldo. I forgot to change that. But anyway, this paper was presented recently in Micro 2022, and is about a different way of doing processing using DRAM computation, or than the ones that we have seen so far in this lecture, including row clone, for example, or ambit or SIMDRAM that was heavily discussed during the semester. So just to start, a quick summary of what this talk is about. So as you should have known at this point, processing memory is really helpful to alleviate data movement bottlenecks for memory-bound workloads. And there are two major types of processing memory systems, yes. Either near memory, where computation is added nearby the memory arrays, or processing using memory, where the characteristics of the memory cells are used to perform some particular type of computation. However, one of the key observations that we did in this work is that the range of the applications that can be executed, or the operations that can be executed in processing using memory systems, particularly processing using DRAM systems, are limited to some set of arithmetic operations or data movement operations, which in turn limits the overall performance or overall range of applications that processing using DRAM can benefit. So our goal is to extend the range of operations that processing using DRAM systems can do, while supporting complex operations like transcendental functions, for example, sine, cosine, logarithmic operations. And to do that, we propose pLUTo, which is a processing using DRAM-based substrate that replaces complex operations with equivalent memory lookups. And to support pLUTo, the key mechanism that supports pLUTo is the pLUTo loop query operations, which enable us to do loop query operations, lookup table query operations in bulk in DRAM. We also extensively evaluate the design space of pLUTo, of the design of a pLUTo loop query operation, and we propose 3 different architectures with different performance, energy, and area trade-offs. And we also propose a system integration solution to integrate pLUTo in current systems, which includes the pLUTo API and the pLUTo compiler. So we extensively evaluate pLUTo, and we show that it greatly outperforms both CPU and GPU-based compute-centric architectures, and also a processing near memory baseline, both in terms of performance and energy, and also incurs small area overhead compared to a baseline DRAM organization from anything from 10% to 23%. And we open source our evaluation infrastructure, and we can check it up in this Safari GitHub repository over here. So this is the outline for this talk. So firstly, I'm going to briefly introduce the problems that we're talking about, then introduce our mechanism, pLUTo, its overall design, and then its system integration. Then I'm going to show a brief summary of our evaluation results, and then I'm going to conclude. So we start with the introduction. So as you know already, data movement is a key bottleneck in today's systems, mostly because of the bandwidth limit memory channel that connects main memory and computer unit of the chip, going to connect off-chip memory to on-chip computer units through a power-hungry and bandwidth limited memory channel. And there is this study here from 2022 that shows that these account for 6% of the total, the energy of moving data through this channel accounts for 60% of the total energy for data-intensive workloads. So to solve this issue, we have processing memory architectures with main philosophies to do computation where the data resides. And there are 2 main ideas to implement processing memory, either processing near memory, where logic units are added closer and closer to the memory device, either in a 3D stack, in the logic layer of a 3D stack memory, or in a nearby DRAM banks, for example. Those are examples that we study in this class this semester. And another example is processing using memory, We are here is a more fundamental way of proposing processing memory because we're not adding any logic to the computation. Instead, we are using the analogical properties of the memory cells to perform some type of computation. So in particular, we are interested in processing using DRAM solutions over here. So we are going to use the DRAM cells to perform some sort of computations. And there are prior works that show how you can do different type of operations using processing using DRAM. As Tabek just talked about, we can have data movement primitives proposed by RowClone, for example, and the other papers that propose copying data across arrays like Lisa paper. Also, you can do bitwise and or not operations as proposed by the Ambit paper. We can extend that to do bit shifting or do arithmetic operations as proposed in the DRAM paper. However, we still cannot accelerate every single type of operations inside processing using DRAM. There are some particular set of operations, for example, transcendental operations that can be approximated using choric arithmetic operations. However, they incur high performance overhead, so they cannot be natively implemented using any of those primitives that prior works have proposed for processing using DRAM. So in the end, we are limited by the sets of operations that we can accelerate. So the goal of this work is to extend the type of operations that can be implemented using processing using DRAM substrate to more arbitrary and complex operations. So with that in mind, I'm going to give a brief overview of pLUTo's key idea and how we implement more complex operations inside DRAM. So here I have an abstraction of how in a compute-centric system or even in a processing near memory computation, how we actually do some computation, right? You have some input data, here X, and then you have some output data that you want to produce. And what we do is that we have some sort of arithmetic logic unit that takes X, transform X by doing some set of computation, and then produces the output in terms of a function of X. Instead of doing that, this is quite unknown at this point. There is another way of doing computation that instead of having a arithmetic unit that is going to transform the input data to produce the output data, we are already going to do this computation. We are going to store in some memory locations, which are called lookup tables, the possible values of the output data of the output that you want to produce based on the input data. So here, what we do is that we input to this table. We do a lookup, a query lookup of the input data X to our lookup table, and then the data is going to be fetched from this memory, from previously stored data in these memory lookups, and then you have your output. So note here that we are not computing anything, or you are not transforming the input data to generate the output data. Instead, we are loading you're loading data to produce the output data. And this is the primary primitive that we are going to exploit here in pLUTo. We are going to replace computation in forms of arithmetic operations with memory access in terms of memory lookups or lookup tables queries. And this is and then you are going to call this operation a pLUTo lookup query operation. So I'm going to illustrate with a more concrete example how a pLUTo look query operation is going to be performed. So let's assume that you want to have a query that is going to store in DRAM a sequence of the prime numbers, the natural prime numbers. And we want to do a pLUTo lookup query that is going to return the second, the first, the second, and the fourth prime numbers. So this should be, if I'm not mistaken, 3, 1, 3, and 5. But maybe don't quote me on that. We're going to see later on. So yeah, I'm correct actually. So here, how it's going to operate is that we are going to take the query, the data that you want to input as an input vector, and then you also have our lookup table, which holds both the sequence of prime numbers, natural prime numbers. So the first prime number is 2, the second one 3, the third one 5, and the fourth one 7. And then you are going to index. We are going to store this in some memory units, and then you are going to index them from 0 to 1. So the input vector that you're going to construct here are going to represent the index of this lookup table. So the second prime number as represents the first index here in my memory. The first prime number is the index 0, and then the second prime number again 1, and the fourth one 3. And then the output that we want to provide is also going to be in terms of the LUT index. So you want to find the LUT index that are going to give us so no, it's going to be in terms of FOI based on the input vector that we input. So how this is going to execute? And this is story memory. So how the operation itself executes. We are going to iterate each one of those elements in the input vector at a time, and then you are going to populate our output vector. So the second prime number, which is stored in LUT index 1, output us to the value of 3. The first prime number, which is stored in LUT index 0, is output us the value of 2. And then the second one is again stored in LUT index 1, and this is going to give us 3. And the final one is going to give us 7. And you want to do this operation in DRAM. We want to exploit the DRAM parallelism to do this LUT query operations. So I'm going to explain how the main structures that PLUTo leverage to do this PLUTo LUT query operation in DRAM. We start with our input vector, which is going to be stored in a DRAM subarray. And then you are going to have an output vector, which is also going to be stored in another DRAM subarray. And in the middle, you are going to dedicate a DRAM subarray to store the LUT. Multiple copies of the LUT that stores the values of the prime numbers here in this example. And note here that the LUTs are stored vertically, so we can exploit the parallelism of DRAM. Other than that, we are going to have some match logic that's going to match the data in each row of our LUT with the data in the input vector. And finally, we are going to have this is one particular implementation of PLUTo, but we are going to have some transistors that are going to be enabled based on the output of the matching logic in case we have a matching between the input vector and the data store in each one of the DRAM rows. Finally, we also have some modifications to the special row decoder that now each row in the DRAM subarray is going to represent an index of the LUT that we are going to do the computation on. So how this all of this is going to work, how the PLUTo LUT query operation is going to work, is going to be via a new DRAM command that you are implementing that is called the PLUTo row sweep operation, which has the ability to enable subsequent DRAM rows with activate subsequent DRAM rows with a single DRAM command. So let's illustrate how this is going to work. So first, we issue a PLUTo row sweep operation, which is going to enable the first DRAM row in the that store or the first copy of our lookup table. Since the data is going to be activated, the DRAM row is going to be activated. Its data is going to be copied to the DRAM row buffer of that particular subarray, and then we are going to start doing the matching computation between the data store. The index of this row, so here 0, and the values is stored in the subarray in the row buffer with the input vector. Basically, the question that the match logic is going to ask is if I'm accessing. So here, if I'm accessing the second prime number, which is stored in row ID 1 for this first element over here. So the first element is storing 1. So 0, my row index here is different from the input vector 1. So this first element is not going to activate one of its corresponding row switch. Then I have the second element here in the input vector 0, which and then I check if my input vector corresponds to the row ID that I'm accessing. So 0 is equal to 0, yes. So it means that is a match, and then I'm going to copy the data from the row buffer that stores the input from the LUT to the output vector. And then I do this for each one of the elements. Again, I'm asking is this one equals to my current row ID? So is equal to 0? No. And 3 is equal to 0, also no, so no data is copied. So this process is going to be repeated throughout every single one of the rows in my lookup table. So the next one, for example, I activate the row with ID 1, and the data is copied to the row buffer. And again, the match logic is going to identify the elements that matches the row ID together with the input vector. And then in the data that it represents a matching is going to be copied to the output vector. So in this case here, in the third case, there is no matching. So there is no in the input vector. I'm not looking for the third prime number. So no element is going to be copied to my input vector. And finally, I have the last one, that is the fourth prime number with 7, which is going to be able to match. We're going to provide a match with the last element here, which is 7. And at the end of the computation, I have in my output vector the output of my LUT query, which was asking for the second, first, second, and fourth prime number, which is 3, 2, 3, and 7. So depending on how you want to implement the match logic to design pLUTo, we can have different trade-offs in terms of performance, area, and throughput. So we propose 3 different architectures that I'm not going to show in details over here today, but I'm going to briefly talk about their trade-offs to implement the matching logic that is required to do this type of computation. So we have our first design, which is called BSA, Buffered Sense Amplifier, which is exactly what I just mentioned before. We have another design, which is called Gated Sense Amplifier, which is going to basically remove the need for extra buffering. And then we are going to have the third design, which is called Gated Memory Cell, which is going to use an extra transistor again to reduce the requirement for the partial data. So in terms of trade-off, in terms of performance, energy efficiency, and area efficiency, we have that the first design, the buffer sense amplifier design, provides medium energy and area efficiency and medium performance. So it's the most balanced design. The gated sense amplifier design provides more area efficiency than the buffer sense amplifier at the cost of lower performance and lower energy efficiency. And finally, the third design, the gated memory cell, provides the highest performance and the highest energy efficiency at the cost of the lowest area efficiency. So in summary, the pLUTo designs that that implement in our paper cover a large design space, and then the user can decide what is the most interesting point for a particular design of the post-use memory operation. So we also propose some system support to integrate pLUTo into commodity systems, and this involves pLUTo API that the user can use in C-like code. And then we have also a pLUTo compiler, which translates the pLUTo API calls into pLUTo ISA extensions. And then we have a control unit that is going to take the pLUTo ISA operations and is going to execute the computation in the pLUTo lookup table operations transparently in DRAM. So this is a quick overview of how all of those components looks like in example C codes, how it's translating to pLUTo APIs and pLUTo ISA instructions, and how the pLUTo controller handles the execution. And for more information on that, I invite us to check in our paper. So finally, our evaluation. So we are going to do evaluations mostly in simulations, and we are going to have as baselines a real CPU and a real GPU and a simulated process-near memory architecture. In terms of our pLUTo simulator is an in-house open source simulator, which you can check in our Safari GitHub repo. And we are going to, our evaluation is quite extensive in the paper. We have performance, energy, area evaluations, circuit reliability and correctness evaluations, and many other design points that we evaluated in the paper. So talking about the workloads that we evaluated, we have 7 real-world workloads, which our main operations cannot be implemented by prior processing using DRAM architectures, basically because they do not support the operations that those applications are going to execute. And we have 4 synthetic workloads that which operations are supported by other processing using DRAM systems. And then you compare both of them. So to summarize, in terms of the speed up compared to all of the 7 workloads, and compare with the 3 different pLUTo architectures that we proposed, the gated subarray, gated sense amplifier, the BSA and the GMC, sorry, we have that the performance increases, as I showed in the design space exploration. The performance of the GSA is the lowest compared to the CPU, but it increases further when you go for the BSA design and even further for the GMC design. And this trend is consistent across every single one of the baselines that you evaluate. So the CPU, the GPU, and the processing memory system. So the main conclusion here is that pLUTo can significantly outperform both the compute-centric organization architectures, CPU and GPU, and processing memory baselines. And if you normalize the performance to the area, we see similar trends. So the performance improves as we change the pLUTo design. And since we are normalizing here through based on the area overhead, the area of the system, we see that pLUTo can provide substantial higher performance per unit area compared to both CPU and GPUs across all of the pLUTo designs. And in terms of energy consumption, again, similar trends. And the main conclusion here is that pLUTo can provide, can reduce energy consumption compared to all of the processor-centric architectures across all of the evaluated workloads. And there are more results in your paper. We have comparison against FPGAs, area overhead analysis, circuit reliability correctness, how we can exploit subarray level parallelism, the cost of loot offloading, and a more complete analysis of the range of support operations. So before I conclude, I'm going to see if there have any questions. Sure.
Talking about FPGAs, I mean, this is similar, this lookup table-based execution is similar to how FPGAs work. Have you looked at if it's possible to implement something like an FPGA in DRAM with this approach?
There are actually a paper that does that, exactly that. It implements a 6-input lookup table, which is exactly what FPGAs do, using DRAM itself. And the goal there is a bit different than pLUTo. pLUTo wants to extend the operations of processing using DRAM. Over there, the goal was to let's implement FPGA architecture using DRAM cells. And then there is some intersection between those two for sure, but it's a bit different. I think the name of the paper is is DARL or something like that. I can post on the YouTube chat later on and on Zoom. But yeah, there is PriOx that does exactly that. And then they use the same type of tools, the gate listing and data placement and routing that FPGAs themselves uses. So yeah. Any other question? Sounds good. So in conclusion, so the goal of this paper is to extend the applicability of processing using DRAM substrates to more complex operations. And we do this via the pLUTo table query operations. We propose 3 different pLUTo designs, which have different trade-offs in terms of performance, energy, and area overhead. We also propose a system support, which includes APIs, compilers, and controllers to facilitate the adoption of pLUTo. And our evaluation shows that pLUTo can greatly outperform CPU, GPUs, and processing memory baselines in terms of performance and energy, while having small area overheads. So thank you so much for listening, and that's all from my side. Is there any other question? Okay, thank you so much.
Thanks a lot, Geraldo. I think we can have a 10-minute break before starting. Thank you.
I should be unmuted, or am I muted on Zoom also? Test, test. Yeah, it should work, I think. Yeah. Thanks, Gira.
Okay, great. So the next talk is for Morpheus. It's another paper in Micro 2022, and Joel is going to present that. Joel is a PhD student in Software Research Group. Joel, feel free to start. Thank you.
Thanks, Mohammed. Good afternoon, everyone. So yeah, as Mohammed said, I will present to you our work Morpheus, extending the last level cache capacity in GPU systems with idle GPU core resources. And we presented this fairly recently in a micro in Chicago. So let's dive right in and go over a high-level overview. So to motivate our work, we study memory-bound GPU applications, and we observe that they leave some cores underutilized. And our goal is to leverage underutilized GPU cores to boost the performance and energy efficiency of memory-bound GPU applications. So to this end, we propose Morpheus, the first technique that leverages some GPU cores' private memories to extend the total GPU last level cache capacity. And to this end, Morpheus employs a software helper kernel in cores and a new hardware unit in LLC partitions. We will get to it, what these terms exactly mean. Morpheus significantly improves performance and energy efficiency of memory-bound GPU applications and enables up to 4x larger LLC with the same conventional LLC hardware. So with this short introduction out of the way, let's go to a more in-depth introduction and motivation. To motivate our work, as I already mentioned, we study memory-bound GPU applications. So what we did is we took a bunch of applications and we looked at the speed up, here plotted on the y-axis, that we get for increasing number of GPU cores that we use for the applications on the x-axis. And if we study a memory-bound application like PageRank, so it's a well-known search algorithm, we get a plot like this. So what you can see is on the left, there's some number of cores. So here up to 40 cores from which we get good performance benefits. And then from 40 to 60 cores, we see little to no performance benefit. Now we repeat the study for an entire range of memory-bound applications. And we see the same pattern in general. So there's good performance benefit from the first few cores, and then little to no performance benefit from the remaining cores. So we conclude that conventional GPUs do not benefit from all cores for memory-bound applications. So if we have a set of GPU cores from which we get good performance benefits, and this other set of GPU cores from which we get little to no performance benefit for memory-bound applications, then our goal is to leverage these underutilized cores to boost the performance and energy efficiency of memory-bound applications. Okay, so this is our goal. Now, to this end, to achieve this goal, we propose Morpheus. So on the left, we draw the on-chip memory of a conventional GPU. So this has well-utilized cores private memories, underutilized cores private memories, and the conventional LLC. On the right, we draw the on-chip memory pictorially of a Morpheus-enabled GPU. And as we can see, it uses the same well-utilized cores private memories and conventional LLC. However, the key difference here is that with Morpheus, the underutilized cores private memories get converted into extended LLC. And this is Morpheus' key idea, repurposing underutilized GPU cores private memories to extend the GPU's total LLC capacity. So far, so good. I claim we can somehow do this. One more thing that's maybe necessary to look at is, would this even help with performance and energy efficiency if we had more LLC? So we did such a study in our work. So we took all our memory-bound applications and we looked at 3 configurations. So we took a GPU with a baseline amount of LLC. This is labeled 1x LLC up there. And then we plot, so we normalize to this throughput, basically, normalized IPC. And then we plot the performance of a twice increased LLC and a 4x increased LLC for these applications. And well, I mean, as you could imagine, right, having more cache helps you with memory issues generally. So, and we can quite consistently see that there's significant speedups. So this can be as much as more than 2x for some applications if you have a 4x larger LLC. So you could say, okay, you expected this kind of plot, but it's good to know that indeed increasing cache will give us extra performance when we manage to do it. So this is the second motivational study we needed. Okay, so we validated that at least if we can make this idea work, then we should get performance benefits somehow. Now, let's see how to implement this idea. So in Morpheus, we propose 2 execution modes for each GPU core. Compute mode on the left and cache mode on the right. Cores in compute mode operate conventionally. So they use their execution units, that is, their functional units, to execute an application kernel. And they use their private memories to keep application data. So private memory in a GPU core here is L1 cache, shared memory, and register file. If a core, in contrast, operates in cache mode, it lends its private memory to extend the LLC. So it uses its function execution units to run something we call an extended LLC kernel. So we propose this new software, and it uses its private memories to keep a controller state, tag array, and data array of this extended LLC. Okay, so we introduced these 2 modes. Now let's see how in a full GPU system Morpheus serves a request. So we have some cores operating in compute mode and some cores operating in cache mode. And these cores are all interconnected through an interconnection network through a set of LLC partitions. Now, applications running on cores in compute mode can generate LLC requests. And any such LLC requests would move over the interconnection network to an LLC partition. That gets first handled by the Morpheus controller, a new hardware unit we propose. And this Morpheus controller makes a forwarding decision. So it decides to either query the conventional LLC, or alternatively, it sends the LLC request over the interconnection network to a core operating in cache mode. So this is equivalent to querying the extended LLC. The extended LLC can then do its software thing, serve the request, and the response to the request is then returned over the interconnection network back to the Morpheus controller, and from there to the core operating in compute mode. So we have kind of this bouncing back and forth action over the Morpheus controller going on. So this is it for the kind of total GPU view. Now let's look at some of these components in some more detail. So we have the Morpheus controller, and afterwards we look at this extended LLC kernel briefly. The Morpheus controller should handle 3 tasks, as I just showed you on that high-level overview. It should first make a forwarding decision. So should we query conventional or extended LLC? And then, depending on that forwarding decision, it should actually query somehow the conventional LLC or the extended LLC. Now, for the forwarding decision, we propose a mechanism which we call address separation. This is a very simple mechanism, and it can just be implemented as combinational logic. Querying the conventional LLC, it's, well, I mean, as you can see there in the number 2 up there in the drawing, this Morpheus controller is kind of physically co-located with the conventional LLC. So querying the conventional LLC is kind of just some forwarding. It's really simple, right? It's directly there. In contrast, querying the extended LLC is at least not straightforward, because somehow there has to be some communication from the Morpheus controller over the interconnection network to the core operating in cache mode. And it's at least not immediately clear how to implement this in an existing GPU. So we propose some mechanism which we call a warp status table. And the high-level idea there is that, okay, we have some core in compute mode and cache mode, the core in compute mode generates LLC requests, and it writes to this warp status table in the Morpheus controller. So this is a new component of this hardware unit. And this warp status table just tracks any ongoing requests on a per set basis and keeps information such as, is the request a read or a write? What was its tag, or is it a hit or a miss? Now, the very crucial part here is that this entire warp status table, it's really just the table, is memory mapped. So you have some SRAM there, but it's memory mapped. So the core operating compute mode can write to this table as with any regular memory access, a regular memory instruction, right? There's no, if you write this in CUDA, it's just an array access basically. So this handles this side of the communication, and the same thing goes for the other side. So regular load and store instructions enable the core operating cache mode to talk to this warp status table and interact with it. So for example, to answer to a request, so to send a response, it just writes into the warp status table, hey, by the way, this is the data of the cache block you requested, it's served now, it was a hit. Or well, if it's a miss, it would just set the bit there. I didn't find it. So this handles actually already the entire communication aspect of Morpheus. And with that, let's look some more at this extended LLC kernel. So the thing that runs on the cores in cache mode. So recall that cores in cache mode should again handle 3 tasks. So yeah, they should repurpose, let's see, the private memories to extend the LLC, and they should do this in 3 ways basically. When they receive a request, they should either query the L1 cache with the request, they should query their own shared memory, or they should query the register file. Now, the key point here is that this should all happen as in a regular kernel. So this kernel that we're proposing should not require any modifications to the GPU core at all. We would like to keep the existing GPU core without any changes and implement all of this functionality still. Now, doing this for the L1 cache is simple. It's an actual cache. So to serve a cache request, you just directly look up that address in your cache that you already have, and the hardware handles everything. Right? It does the exact same operation. Creating a shared memory is just a scratchpad space that you can access from software. So there's some software engineering needed there, but it's not conceptually difficult. Right? You just write some code, write a cache, use this as your memory for your cache, and it's golden. What's not so clear is how to do this with the register file. So the register file is typically not accessible or indexable like regular memory. Right? In your code, basically a register is always an immediate value. So you cannot say, give me the i's register where I is the value of another register. You can always only get the third register. So we need to figure out how to do this somehow, and we need to figure out how to do this efficiently. So what we figure out is we can actually, thanks to this SIMD parallelism of GPUs, we can get really nice data layout across threads and get really high efficiency with a lot of parallelism. So how we do this is to implement one extended LLC set. We have a, let's see, one extended LLC set contains 32 cache blocks. And we implement this extended LLC blocks, let's see, with 32 threads. So recall that one warp in a modern CUDA, modern NVIDIA GPU consists of 32 threads. And then we can have this really nice mapping where each thread simply is responsible for holding one tag, right? And one tag in turn belongs to one cache block. So when we then get a request for some query tag, each thread just goes and checks, well, is my tag the same as the query tag? So they compare, and well, if it's the same, they say, yes, it's mine, I serve my block, fine. And there's some, let's say, efficient CUDA programming needed in terms of how you actually serve this block, and there's an interesting part in our paper about that, but let's not go into it right now. But the really efficient part about this is if you have this layout, you have 32 threads operating in parallel. So effectively, from software, you have a 32-way parallel tag matching operation. So this is for one extended LLC set. Now, in reality, in a GPU, we can have many warps in hardware. So to really use the full bandwidth of our GPU core, so we can have multiple extended LLC sets. So each set is implemented by one warp. We have multiple warps operating in parallel. This gives us a second level of parallelism. So overall, we have 2 levels of parallelism. Threads operating in parallel within a warp, and then many warps operating, so this could be as many as 48 in reality, operating in parallel, serving requests to different LLC sets. So these 2 levels of parallelism give us really high efficiency in this extended LLC kernel. Okay, how are we doing? We're doing fine time-wise. Good. So well, we have covered the base functionality of Morpheus, right? We have looked at this high-level view of how a request gets served across the entire GPU. We have looked at exactly how the Morpheus controller uses the warp status table to enable communication. We have looked at the extended LLC kernel and how it uses parallelism really efficiently to get high throughput. So we have the base functionality there for Morpheus, but now we propose several optimizations to make this work particularly efficiently. One that I find personally very interesting in particular is hit-miss prediction. So let's look at this as a bit of a case study. So I'm showing here on the x-axis time, so essentially latency for a single LLC access. And each, let's say, possible scenario consists of these little blocks, which each correspond to one part of the operation. So we could have first some time spent on the interconnection network, and then some time spent in the Morpheus controller, and then some time spent for a conventional LLC access if we hit in the conventional LLC. And if we hit in the conventional LLC, then this request is immediately returned over the interconnection network to a core, and it's done in fairly short time, so 161 nanoseconds. If we miss, well, we get a much longer block here. It's not just returned directly, because after we see in the green part that we miss in the conventional LLC, we now query off-chip memory, right, GDDR. So now the request takes much longer, so something like 600 nanoseconds. Fine, that's what happens in a conventional GPU also. Certainly what's desirable is that when we hit in our extended LLC, our new software-supported extended LLC, we get lower latency. So we do more round trips over the interconnection network, but actually serving the access is much faster than off-chip memory. So we get in total something that's less than off-chip access in the conventional LLC. That's good. Now here's where it gets painful. An extended LLC miss. In the extended LLC miss means we first spend time going over the interconnection network to the Morpheus controller, from the Morpheus controller back to a core over the interconnection network, trying to check the extended LLC in that core, back over the interconnection network, realizing that we missed in the extended LLC, then going after all to the off-chip memory, and then back to the core that requested originally the address. So this is really painful. Many round trips over the interconnection network, plus an off-chip memory access, and in the end, we're even slower than if we just had a conventional GPU. Right? This is the worst case scenario with our new proposal. So what we saw is that it would be really nice if at least we could save us these round trips, right? If we miss, and we could do a prediction, let's say we have an oracle that predicts, by the way, your data will not be in your extended LLC, then we can immediately here go to off-chip memory and not spend this extra time over in the connection network and so on. And then actually our access is again comparable to, just a conventional LLC miss. So this is what you would desire, correctly predicting the extended LLC miss. And well, correctly predicting them can reduce any latency issues we may have. So we come up with some hit-miss predictor design. And well, there's some flowchart there we have from the paper. You don't need to read it in detail right now. But the key point here is we come up with some, I would say, fairly simple mechanism based on Bloom filters. I guess you saw Bloom filters being used in many works so far. We needed some fairly specific correct guarantees from the Bloom filters for correctness. So we somehow needed to avoid ever getting false negatives, because otherwise somehow we would get sometimes invalid data in our cache. So we came up with this mechanism for Bloom filters, but in the end it's still fairly simple, and you could come up with much smarter strategies here. So at this point, let's try something interactive to wake everyone up. Hit-miss predictor. It should hopefully ring a bell. Do we know of any more sophisticated hit-miss predictors? You might have seen a presentation in one of the recent research lectures also. So if it doesn't ring a bell, maybe this helps. So Raoul presented this. Actually also a micro. And this is Raoul presenting the Hermes store or Hermes store to us. Well, or maybe he presented his paper also. His paper where he does off-chip load predictions using perceptrons, right? Well, he won best paper award with this actually. This is a much more sophisticated mechanism of this Bloom filter-based mechanism. His proposal is for CPUs, but the point is somehow it appears that CPU, GPU appears quite connected, and well, I guess one at this point has to raise the question, maybe in the future, it would be interesting to see what Hermes would do for a GPU also, right? It's a longer discussion. I think we have many more interesting and exciting mechanisms in our paper. So, of course, we explain the mechanisms that I explained in much more detail. And then we have also more optimization techniques. Among the hit-miss prediction that I just showed, we propose some new GPU instruction, which we call indirect move, which enables exactly to not have registers only accessed by immediate register indexes, and then how to apply cache compression to Morpheus. This also works surprisingly effectively, actually. And in the end, with these optimization techniques, we really get good performance from Morpheus. So let's look at that briefly. So we evaluate on the 17 applications, the 14 memory-bound ones that I already showed, and then so the compute-bound applications, just to know if we lose performance for compute-bound, if we do lose performance or not. So we experimentally characterize the extended LLC. This happens on a real GPU, actually. This is not all just smoke and mirrors evaluation. So part of this evaluation we can run on a real GPU, even though we're missing some of the hardware units. And then for the parts of the evaluation in which we really need the hardware for, we simulate it in a state-of-the-art GPU simulator. And we plug the numbers that we get from our real system into our simulation. So we plot on the y-axis here normalized execution time of several applications. So lower is better. We take our 17 applications, and we take as a baseline, we normalize to this one, an off-the-shelf NVIDIA RTX 3080 GPU. And this is unmodified, the thing you can actually buy in the store. And then we take as a, let's say, an ideal baseline, we take a 3080, which just has a 4x larger conventional LLC. So it gets way more LLC capacity for free, basically. This is our ideal baseline. And then we compare Morpheus. And as you can see here, first, Morpheus performs better than or equal to the baseline for all applications. Second, on average, Morpheus accelerates memory-bound applications by 39%. And third, actually, Morpheus is quite close to this 4x larger conventional LLC. So it's within 3% on average. So the key point here is that Morpheus doesn't have this huge conventional LLC, but still gets almost all of the performance without that extra cost. We do a similar evaluation for energy efficiency. So performance per watt on the y-axis, higher is better. We take the same baselines and Morpheus. And we again see, okay, Morpheus is always more energy efficient, or at least the same energy efficiency as the baseline for all applications. And then on average, Morpheus improves energy efficiency by 58% for memory-bound applications. And finally, Morpheus, again, is very close to this much more expensive conventional LLC. And by the way, when we plot this energy efficiency here, we didn't even consider the extra energy cost of this larger cache. So we assumed kind of we get a 4x larger conventional LLC for free, and we're still within 6% with Morpheus. So I think in conclusion, we can say Morpheus works quite effectively there, and we have a much more in-depth evaluation where we characterize every detail of this Morpheus proposal, including the extended LLC on a real GPU, performance and energy comparisons with multiple variants of Morpheus and more baselines, the total LLC throughput, on and off-chip bandwidth utilization, and then power overhead and memory overhead analysis. So let me conclude very briefly. We observed that memory-bound GPU applications leave some cores underutilized. Our goal was to leverage the underutilized cores to boost the performance and energy efficiency of memory-bound applications. To this end, we proposed Morpheus, the first technique that leverages some GPU cores' private memories to extend the GPU last level cache capacity. And we observed that, well, Morpheus outperforms state-of-the-art GPU architectures, such as by 39% in terms of performance, 58% in terms of energy efficiency, and gets even within 3% performance of a 4x larger conventional LLC. And finally, Morpheus provides 4x more LLC capacity while using the same conventional LLC hardware. So we conclude that Morpheus effectively repurposes the private memories of underutilized cores to extend the GPU LLC capacity. With that, I thank you for your attention, and I'm happy to take any questions.
Thanks a lot, Joel. Is there any question? So I think I am going to ask a couple of questions, Joel. Thanks a lot. So the target of Morpheus is for memory-bound applications. Do you think Morpheus can be also useful for compute-bound applications?
So we showed that at least Morpheus on the applications we evaluated, Morpheus at least doesn't cause slowdown. That's for sure we can say. I think potentially so what we do is we have, as part of our methodology, is we optimize basically this number of cores in compute, number of cores in cache mode, to the point where we get the optimal performance. So we try to trade off number of cores that give us extra cache capacity or number of cores that just do computation, and we take the best one. And what we see is for compute-bound applications, actually, at least in the ones we evaluated, we got the best performance every time by using zero more extended LLC cores or cache mode cores. There might be some corner cases of compute-bound applications, though.
I'm mostly thinking of improving performance of compute-bound applications. So imagine people integrate Morpheus while they are designing GPU. So basically, it's a new dimension, right? So we show that Morpheus can provide very good performance of the, for the larger LLC cache. So
I think it becomes a different dimension if we consider applying Morpheus let's say for new design trade-offs, right? So we can consider, for example, having less LLC capacity. So assume you have some area budget for your GPU. Say you have 100 square millimeters for your GPU die. If currently, I don't know, 50%, don't quote me on that number. If currently assume 50% of that die is used for LLC capacity, then with a proposal like Morpheus, what you could consider is actually provisioning less conventional LLC. And instead, for example, use only 25% for conventional LLC and then use this extra 25% for more compute cores. Right? In that case, you could increase the performance of compute bound applications.
Yeah, exactly. Another question I have is, so for the address mapping, as far as I know, in this paper, we use static simple address mapping, right? Between extended LLC and hardware LLC. Can you imagine, I mean, more intelligent address mapping and basically how useful they can be?
I cannot give you an estimate for in terms of how useful that can be, but for sure, you can consider more smarter address mapping than static. For example, right now, what you could consider as a worst case scenario would be that you have somehow, due to your static mapping, you have a lot of conflicts somehow through your application. You have a very unfortunate memory access pattern, you get conflicts. Then we would benefit from a smarter pattern. Clearly, for the applications we evaluated, we still saw that even this simple pattern works to give us very good benefits. But yes, for sure, in the future, having smarter non-static mechanisms might provide benefits.
Yeah, exactly. And also, I can see extended LLC accesses, they are slower. So someone can think of, allocating those requests that they are latency sensitive to hardware LLC and the other to extended LLC, which is a bit, not easy to imagine for GPUs because, mostly the application in data is data level parallelism. So,
I think one, so I can't quote you the unfortunately the work right now, but there's also been proposals of replicating data in cache to have basically higher bandwidth. So if you get a lot of bank conflicts for some LLC cache data, you could consider replicating data in your cache and combining a proposal like that with Morpheus, where some of your data is replicated in the conventional LLC and some of it is replicated in the extended LLC might also be interesting. And again, of course, not in a static manner necessarily.
Perfect. Thanks a lot, Joel. Giray, do you have a question? Yeah.
Thanks a lot then.
Perfect. Thank you, Joel.
Okay, it's unmuted now. Are these slides visible on Zoom?
Yes, they are invisible on Zoom.
Okay, perfect.
Okay, so the next talk is about a deeper look into RowHammer's sensitivities. Giray is going to lead discussion on this paper. Giray, as you probably know, he's also a PhD student in Safari Research Group. So feel free to start. Thank you.
Okay, thanks, Mohammed. I hope we have enough time. Is it 3 now? Okay, so we have around like an hour, I guess, right? Anyways, it's not going to take that long. So last week I presented another RowHammer characterization work actually about scaling down the word line voltage and its effects on RowHammer. And over there, I actually referred to this other paper. So this is a paper which is a year old. So it's published in Micro 2021. It was like October in 2021. And I collared this paper with Luis Orosa, who is in Galicia Supercomputing Center now. Okay, so we have a little bit of a DRAM background again. So this is the DRAM module, as you know from the past, and in each chip in this module, we have multiple banks, and each bank has multiple subarrays. And within subarray, we have two-dimensional DRAM cells that are accessed in row granularity using word lines, and each cell is connected to the row buffer using bit lines. I think I can use this. Okay, so again, here's a DRAM cell. We have capacitor and access transistor connected to a bit line, and access transistor is driven by the word line. And to access data, okay, before accessing data, in DRAM cell, we have this intrinsic characteristic of charge leakage. So there are like several charge leakage paths here, and you store data as voltage here, and over time you lose this charge and you lose your data. So to avoid that, you need to do refresh, which restores the capacitor voltage with a time period called refresh window. And other than this, so this is the main maintenance operation here. To access data in DRAM cell, we need to first activate the row that contains data. And then we need to do some column accesses that are serviced from the row buffer. And then to access data in another row, we need to basically pre-charge the row or pre-charge the bank and close the row, and then prepare the whole bank for the next row activation. And this is another recap of RowHammer vulnerability. So say that our data is in row 2, so you need to open this row to access data, and you close it after you're done with row 2. And if you do this operation many times, activate pre-charge, you see bit flips in the adjacent rows. And if you keep doing that more times, then you see more bit flips in more rows. And this phenomenon is called RowHammer. And we identify the row that we keep opening and closing as the aggressor row, and the rows affected as victim rows. Okay, so with this background, let's move to the motivation. So denser DRAM chips are more vulnerable to RowHammer. This is shown by some previous words. And understand RowHammer can enable effective and efficient solutions. But unfortunately, we don't have any rigorous study that demonstrates this vulnerability, how this vulnerability varies under different conditions. So we look at 3 conditions here. I'll mention it in a bit. So our goal in this work is to provide insights into 3 of these fundamental properties of RowHammer that can be leveraged to design more effective and efficient attacks and defenses. So the first one is DRAM chip temperature. The second one is the time that an aggressor row stays active during the attack. And the third one is the victim DRAM cell's physical location. So to do this investigation, we present the first experimental study that uses 270 DRAM chips from 4 major manufacturers. And we provide several key takeaways and novel observations. But here, to summarize all of them, we can say a RowHammer bit flip is more likely to occur in a bounded range of temperature if the aggressor row is active for a longer time and in certain physical regions of the DRAM module. So we conclude that our novel observations can inspire and aid future work to craft more effective attacks and design more effective and efficient defenses. Okay, this is the outline, and this is the motivation. This is RowHammer, and as we know, the RowHammer is getting worse. If you look at the minimum activation count to observe a bit flip, it got reduced more than an order of magnitude in less than a decade. So it keeps reducing. And the defenses are becoming prohibitively expensive, as shown by the prior work, and we need a deeper understanding of this phenomenon. Unfortunately, no rigorous experimental study investigates how some fundamental properties of RowHammer can affect RowHammer vulnerability, and how can we use them to find effective and efficient solutions. So to this end, it's critical to gain insights into RowHammer and its fundamental properties. And our goal in this paper is to provide insights into 3 of these fundamental properties. The first one is temperature. Second one is, you can say, access pattern, but in particular, we focus on aggressor row's active time during the attack, and the location of the victim DRAM cells, physical location in the DRAM chip. And we do this to find effective and efficient attacks and defenses. Okay, so this is the infrastructure, which is very similar to the one that I explained last week. So we have actually 2 different infrastructures for this paper. We test DDR3 and DDR4 modules. Both of them are some FPGA-based infrastructures using these FPGA models, and they are programmed with a modified version of SoftMC. And as I said earlier, this modified version of SoftMC is now called DRAM Bander. And we have a DRAM module that is clamped with heaters here. And these heaters are controlled by this temperature controller here. And we have the FPGA here with SoftMC, and there's a PCA connection going to the host machine. Okay, so this infrastructure allows us with, provides us with fine-grained control over DRAM commands, timing parameters, and temperature. So to characterize our DRAM chips at worst-case conditions, we first prevent sources of interference during core test loop. And to do that, we disable certain things. First one is no DRAM refresh. So we disable all DRAM refresh operations so that we avoid refreshing the victim row, which can obfuscate some bit flips for us. And we disable DRAM calibration events to minimize variation in test timing. And we disable all RowHammer mitigation mechanisms so that we can observe the bit flips as they happen in the circuit level. And we keep our tests under 32 milliseconds again, so that we don't have any retention failures, and therefore we don't need to do any DRAM refresh. And as the access sequence, we use the worst-case access sequence based on prior worst observations, which is repeatedly accessing 2 physically adjacent rows as fast as possible. So there's an exception here for the second set of tests where we look at the aggressor row's active time. We don't do this. But I'll explain it in a little bit. So in this study, we test DRAM chips from, so we test 272 DRAM chips in total, and they come from 4 major manufacturers. And these DRAM chips implement 2 different DRAM standards, and they have different density, die revision, and organizations. And this is the full paper here. And we have an extended version of this paper in the archive. Actually, you can find more detailed information about these DRAM modules on archive. So let's move on with the first set of tests, temperature analysis. So let's start with the key takeaway of, the first key takeaway. So it says that to ensure that the DRAM cell is not vulnerable to RowHammer, we must characterize the cell at all operating temperatures. And it will be hopefully obvious in a little bit why. So the second takeaway says that RowHammer vulnerability tends to worsen as DRAM temperature increases. However, there are some individual DRAM rows that can exhibit behavior different from dominant trend. So let's look at the data. So here on this line, we have temperature increasing from left to right. And we observe in our chips that there is a lower bound of temperature, and there's an upper bound of temperature where we observe bit flips between these lower and upper bound temperature. And then if you exceed for warmer temperatures on the right or colder temperatures on the left, then you do not observe any bit flips at the same, running the same test, while you're observing bit flips only this range, basically. So we call this range vulnerable temperature range. And when we look at the fraction of vulnerable DRAM cells experiencing bit flips at all temperature levels within their vulnerable temperature range, so they don't observe any bit flips at temperatures lower than the lower bound and temperatures higher than the upper bound. But whatever temperature level we test within this vulnerable temperature range, they observe it, they experience bit flips. And this is the fraction of DRAM cells that exhibit this behavior. So we can say that this is like the mainstream behavior that for almost all of the cells, we have a bounded vulnerable temperature range. And yes, so most DRAM cells are vulnerable to RowHammer throughout a continuous temperature range. And here we have another density distribution plot. So on the x-axis, we see the lower bound of the vulnerable temperature range. And on the y-axis, we see the upper bound of the vulnerable temperature range. And different colors show different fraction of vulnerable DRAM cells here. So it basically shows you the population. And as it goes from like purple to yellow, the population increases, right? And as an example, if we look at like this particular cell or bin here, it means that 0.4% of the DRAM cells are vulnerable to RowHammer from 55 degrees to 60 degrees. So if you test these cells at 50 degrees or 65 degrees, then they don't actually exhibit bit flips at the given activation count, basically. And another example, these 0.5% of the cells are vulnerable from 70 to 85 degrees. So we see that different DRAM cells are vulnerable to RowHammer within specific temperature ranges, which can be different from each other. And as we look at like all data from all four manufacturers, we see some similar distribution across these lower and upper bounds of temperatures. And we see that a significant fraction of vulnerable DRAM cells exhibit bit flips at all tested temperatures. Okay, so from 50 degrees to 90 degrees, we always see bit flips in these these fractions of DRAM cells. And there are also, if you look at like this diagonal, there are also a small fraction of DRAM cells that actually exhibit RowHammer vulnerability at a particular temperature range. So here, for example, this 0.4% is, so both lower and upper bound is 55 degrees here, right? So the cells that belong to this set actually exhibit RowHammer bit flips only at 55 degrees Celsius. And yeah, so here another example, 0.2% of the cells experience bit flips only at 70 degrees Celsius. So as a result of this, actually, we conclude that to make sure that a DRAM cell is vulnerable to RowHammer or not vulnerable to RowHammer, you basically need to test that DRAM cell at all temperature levels that you can test. And let's look at some other general behavior across all DRAM cells instead of individual DRAM cells. So on the x-axis, we have increase in temperature here. On the y-axis, we have the variation in bit flip counts per DRAM row. So this is basically bit error rate on the y-axis, right? So we observe that more cells experience bit flips as temperature increases, even though some of them don't experience bit flips at like higher temperature range, you know. If you look at the overall bit error rate, it increases. And when we repeat this test across all manufacturers, we observe that these chips from these three manufacturers actually exhibit an increase in trend, while the chips from manufacturer B, which is Samsung, actually exhibits reduced in trend. So we say that the DRAM row's bit error rate can either increase or decrease with temperature, depending on DRAM manufacturer. So different manufacturers can have different behaviors. So this is important actually, because when you put your DRAM chip in the field, you might need to understand like at what temperature I need to operate it. So I'll try avoiding boring you with more details about this experiments, but I'll just quickly mention other temperature analysis we have in the paper. So we look at the minimum activation count at which a victim row experiences a bit flip, or as known as HC first, when temperature changes. And we observe that DRAM rows can show either higher or lower HC first when temperature increases. So this is in line with our observations on the bit error rate. And we also look at how much HC first changes by looking at the delta how much HC first changes based on the temperature change or delta temperature. And we see that HC first tends to generally decrease when the temperature change increases. And also we look at delta HC first and delta T, and we see that the change in HC first actually tends to be larger when the temperature increases, the change in temperature increases. So I refer you to the full paper for these in-depth analyses. And I'll move on to the second set of experiments, which is based on the aggressor row's active time. So what do I, okay, let's first give the key takeaways. So the takeaway 3 says, as an aggressor row stays active longer, victim DRAM cells become more vulnerable to RowHammer. And another takeaway is RowHammer vulnerability of victim cells decreases when the bank is precharged for a longer time. So here, this is the exceptional methodology we did, excuse me, only for these set of experiments. So this is our baseline. In the baseline, this is a timeline as we go from left to right, time flows. And in this yellow background parts, we have a row active, right? So let's say we are doing double-sided row hammering, and we are hammering, keep activating and precharging row A and row B in this interleaved manner. And we activate row A, here we precharge, and then here we open row B, here we close, here open row A, and it goes like that, right? So in the first set of experiments, in this part of the paper, we increase the aggressor row's active time. So what does that mean? We actually make this yellow background part longer. So row A is active for longer time. And then we keep this close time the same as before. And then we activate row B, and then we also keep it longer. And we look at the effect of having this kind of access pattern compared to this kind of access pattern on the RowHammer vulnerability. And we have the complementary set of experiments as well, where we actually increase the time where the bank stays precharged here. So here, so we have some box plot here. So in box plot, we see the distribution of these values in each box. So on the y-axis, we look at the number of bit flips per DRAM row. So we look at the bit error rate, every single DRAM row. And we look at the aggressor row active time on the x-axis. So we increase the aggressor row active time. So we keep rows active longer. And we see how bit error rate changes. And obviously, it increases from left to right, right? And the conclusion is the aggressor row stays active longer, more DRAM cells experience RowHammer bit flips. And when we look at this behavior across manufacturers, unlike temperature, we actually see the same behavior across all 4 manufacturers. And here we look at the minimum activation count to observe a bit flip, or the RowHammer threshold, or HC first. And again, on the x-axis, we increase the aggressor row's active time. And okay, maybe it's not very clear when you look at these fat boxes, but if you look at the whole picture, you see that there is a decrease in trend here. And we conclude that fewer activations are required to cause RowHammer bit flips when aggressor rows stay active for a longer time. So this observation also holds for chips across all 4 manufacturers. And we conclude that as the aggressor row stays active longer, more DRAM cells experience RowHammer bit flips, and they experience RowHammer bit flips at lower activation counts, meaning that RowHammer vulnerability simply increases. Okay. So we have more analyses about the tests where we increase the bank precharge time, and we observe that when we keep aggressor rows stay active longer. And also the variation about aggressor row active time. Yes. We have these observations in the paper. So the first observation is that when aggressive row stays active longer, the RowHammer vulnerability constant worsens across tested DRAM rows. So we see a dominant trend over there. And when we look at the pre-charge time getting longer, we observe the opposite trend. So fewer DRAM cells experience RowHammer bit flips, and we need higher activation counts. So it's better to keep banks closed, basically, as opposed to keeping some rows open. So when you keep rows open, your RowHammer vulnerability increases. When you keep banks closed, it decreases. And as the bank stays pre-charged longer, the RowHammer vulnerability consistently reduces across tested DRAM rows. And I'll again refer you to the full paper for details of these analyses and the pre-charge experiments. And here's the last part of the experimental analysis, special variation analysis. So our key takeaway, and the first one is RowHammer vulnerability significantly varies across DRAM rows and columns due to design-induced and manufacturing process-induced variation. And the distribution of the minimum activation count to observe bit flips exhibit a diverse set of values in a subarray and similar values across subarrays. So a subarray is actually can be a representative of the whole DRAM chip or module. Okay, so when we look at the minimum activation count to observe bit flips or HC first RowHammer threshold, we observe that this value decreases as not decreases, sorry. This value varies a lot across different DRAM rows. So we sort DRAM rows based on their HC first value. So this is more like a S curve where you look at the distribution. And our conclusion is that you see some very high RowHammer thresholds here and very low RowHammer thresholds here, right? So there's a huge difference in between orders of magnitude. So the RowHammer vulnerability significantly varies across DRAM rows. So maybe it doesn't make sense to use the same defense for every single row, right? Some of them are definitely more vulnerable than the others. And when we look at this distribution data across different DRAM manufacturers, we actually see that the significant variation exists in all chips from all four manufacturers. And here, again, we have a zoomed in version of the same plot actually. So we look at on the x-axis, these are the percentile values. So on the left, we have 90th percentile, and on the right, we have 100th percentile. So we are looking at the tail of the distribution, the last 10%, right? And we see that even in this last 10%, there's a huge difference between these RowHammer thresholds. And we conclude that a small fraction of DRAM rows are significantly more vulnerable to RowHammer than the vast majority of the rows. So if you actually configure all your defenses or all your system parameters based on the worst case, you're actually overshooting by a lot because more than 90% of the rows are actually like double the hammer count or maybe like triple here, right? Okay, so here we look at the variation across columns. So this is a heat map, and on the color code, we see number of bit flips in a column aggregated across all rows. So we look at how different columns are vulnerable to different, how different columns are vulnerable to the RowHammer vulnerability. And on the x-axis, we see column index, and on the y-axis, we see the chip ID within the module. So as I said earlier, each module has, okay, here we have 8 chips. We also have some modules with 16 chips. So here, oh wait, I'm going backwards. Okay, so here I want to highlight that there are certain points which have like bright colors here and there, like in several places. But there are also very dark regions here, right? So we conclude that based on this observation, this is a bit eyeball statistics at this level. Certain columns are significantly more vulnerable to RowHammer than other columns. And definitely there is a need for a deeper statistical analysis for this. So this is a next step of that analysis, basically. So here we have on the y-axis, RowHammer vulnerability in some normalized metric, and variation across DRAM chips on the x-axis. And we see that high RowHammer vulnerability, we see that some chips show high RowHammer vulnerability, actually all chips, okay. So here on the left, we have a smaller variation across DRAM chips in a module, right? And on the right, as we go right, the variation across DRAM chips increases. And as we go lower, the RowHammer vulnerability is low. And as we go higher, it's higher. So we see that there's some accumulation on like left top corner here, meaning that we have a high RowHammer vulnerability across all chips in some modules, right? And it's actually, when you look at some consistent trend across different chips in a module, it actually points to design-induced variation, because that is the common thing across chips. And also, we observe some modules that have low vulnerability or a little bit higher vulnerability, but a very high variation across different DRAM chips. So for those, we conclude that there has to be some manufacturing process-induced variation, because you implement the same design in several chips, you put those chips into the same module, and some of them turn out to be more vulnerable than the others. And we also look at this variation across columns and chips in across different manufacturers, and we observe that different accumulations here. For example, DRAM modules from manufacturer A actually has some accumulation here, right bottom corner. So this is Micron, and this means that, yeah, so the chips we test from manufacturer Micron actually have a high variation in RowHammer vulnerability based on their manufacturing process variation. But if you look at Samsung, for example, manufacturer B, it's the opposite, right? So this is like half of the chips, and their vulnerability is based on some design decisions. And here is Nanya, for example, it's again manufacturing process variation. So we conclude that both manufacturing process and design can affect RowHammer vulnerability of DRAM chips. And we also look at different metrics in the paper. So we look at the minimum activation count, again, the RowHammer threshold or HC first, across rows in a subarray and across subarrays in a DRAM module. As I said earlier, in a bank, you have multiple subarrays. And we observe that the most vulnerable DRAM row in a subarray is significantly more vulnerable than the other rows in the subarray. So when you look at the distribution across rows in a single subarray, you see a similar distribution as I showed earlier. And when you look at the HC first distributions of subarrays within the DRAM module, you observe that they're significantly more similar to each other than those of subarrays from different modules. So this actually shows an indicator that, okay, yeah, you want to test some DRAM modules, RowHammer vulnerability, you need to profile it. And when you actually characterize one single subarray, it shows you the distribution of, it's a indicator of the distribution you will see in the whole chip. And given that you have like hundreds of these subarrays in a DRAM module, you can actually reduce your testing time a lot by building some confidence on this kind of observation. And again, for details, I'll refer to you to the full paper, and I'll talk a little bit on the implications of our observations on attacks and defenses. So we conclude that on our observations can be leveraged to craft more effective RowHammer attacks and more effective and efficient RowHammer defenses. And I'll show a few examples here. So this is an improvement on attack, for example. So an attacker can manipulate the temperature. So this is our threat model here. An attacker can manipulate the temperature to make cells that store sensitive data more vulnerable. Let's say you have a malicious employee in a data center that can heat up the chip, or maybe you have some chip with processing memory enabled. You can pressurize that chip, put more workload, increase temperature of the chip, and you can make that chip more vulnerable to RowHammer than the nominal voltage, not voltage, temperature. And we observe that DRAM cells are vulnerable in a bounded temperature range, right? So this is, again, a reminder of vulnerable temperature range definition. Let's say that our data is stored in some DRAM cells that are vulnerable to RowHammer between 50 and 70 degrees Celsius. And the operating temperature was 45 degrees Celsius. So you heat up the chip temperature and reach to 55, and you're in the vulnerable temperature range. Or you were at 75, you cool down, and then you reach to 65, and boom, you're in vulnerable temperature range. So you can perform RowHammer in an easier way. Of course, it requires a strong threat model, right? So another example is that maybe you can use RowHammer vulnerability as a side channel to understand the temperature of the DRAM chip. And you can, by doing that, you can identify some abnormal increase in temperature to attack a data centers during its peak hours. Let's say RowHammer is a probe this time. So we keep hammering some rows. We observe the bit flips. And let's say we are in the peak hours of a data center where there is like a lot of loads and a lot of pressure on the machines, and the temperature increased abnormally. And we can actually identify when this happens exactly by looking at RowHammer vulnerability, right? And then we can perform other attacks over there. And we can also precisely measure the temperature to trigger an attack exactly at the desired temperature, because we observed some cells were vulnerable to RowHammer at some particular temperatures. Let's say, yeah, this is a number that I borrowed from manufacturer C's data, I think it was Hynix. So 0.4% of the cells exhibit RowHammer bit flips only at 70 degrees Celsius, right? So if you see a bit flip on those cells, then it means that your temperature is 70 degrees Celsius. It's precisely, you can identify that. Okay, so another attack. So this is the state-of-the-art attack model. You hammer rows as frequently as possible. And then we show that if you, instead of doing that, if you keep aggressor rows active for a little bit longer, you reduce your activation rate. And it actually reduces your minimum activation count to induce bit flip. And it's a significant decrease by 36% here. And if your RowHammer defense mechanism does not account for this, and if you know this access pattern, and if you apply this, then you can reduce RowHammer threshold, like the real RowHammer threshold. But your defense assumes a high RowHammer threshold, and you, boom, bypass defense that do not account for this reduction. So these were some attack improvement examples. So there can be many more, and I guess I'm open for discussion for more improvements. But I'm also going to give some examples on defense improvements. The first example is leveraging the variation across DRAM rows. So as I showed earlier, when you look at the breakdown of DRAM rows in terms of their RowHammer vulnerability, you can, yeah, this is a ballpark number you can get from our experimental data. Like 10% of the rows show some RowHammer threshold, and 90% of the remaining 90% of the rows actually show the minimum of double this RowHammer threshold. If you actually split them into multiple clusters, you will see actually much larger HC first, like order of magnitude larger RowHammer thresholds, right? And if you look at literature, if you look at RowHammer defense mechanisms, you always observe that as RowHammer threshold gets lower, your overheads get higher. And because this happens because at lower RowHammer thresholds, your mechanism needs to be more aggressive. So by leveraging this variation, you can actually say that, okay, for 90% of the rows, let's not be that aggressive because it's not required. And you can reduce the area reduction of these two RowHammer mitigation mechanisms, for example, significantly by doing this. You can also save some performance overhead, for example, if you're using PiDRAM, right? It's definitely possible. And it's very doable, actually. Another example is leveraging variation with temperature. Let's say you have some DRAM cells experience bit flip at a bounded vulnerable temperature range again. And you measure your temperature using your temperature sensor in your system. And let's say you're at this location, at V here, for example. And you can say that, okay, yeah, so, or maybe, yeah, I should describe here. Let's say you have row A and row B that show like different vulnerable temperature ranges here. Then you can actually disable row A and disable row B, like at these vulnerable temperature ranges. You can use row A here instead of row B, and here row B instead of row A, so that you can actually reduce your vulnerable to RowHammer in high level. So there are more defense examples in the paper. Another one is leveraging the similarity across subarrays, so that you can reduce the module's profiling time, as I explained earlier. You can monitor and limit the aggressor active time from memory controller. And if you notice that some rows are being active for a long time, then you can reduce RowHammer vulnerability by closing those rows, for example. Or you can modify your defenses to be more proactive for those rows. You can also implement some ECC schemes that can target the non-uniform bit-error distribution caused by design industry variation in some DRAM columns. So, because experimental data shows that some DRAM columns are more vulnerable to RowHammer, right? So maybe you can craft a special ECC scheme for those particular columns. And if you're not using Samsung, basically, cooling DRAM chips can reduce overall bit error rate. So it's always a good idea to cool down the DRAM chips if you're not using Samsung. Okay, so to conclude, our motivation was that the denser DRAM chips, I mean, the RowHammer vulnerability increases over generations, and we need a better understanding to find effective and efficient solutions. But there were no rigorous study demonstrating RowHammer vulnerability under different conditions. So in this study, we looked at DRAM chip temperature, aggressor rows on time, and DRAM cells physical location on 272 DRAM chips from 4 major manufacturers. And we show that a RowHammer bit flip is more likely to occur in a bounded range of temperature if the aggressor row is active for a longer time and in certain physical regions of DRAM module under attack. And we conclude and hope that our novel observations can inspire and aid future work, craft more effective attacks, and design more effective and efficient defenses. And that's the end of my talk. And I hope I didn't, I took a lot of time actually. Sorry about that.
No, no.
Do we have questions?
That was great. Thanks a lot, Giray.
Sure.
Any question?
Please go ahead.
So what causes bit flips? What is your guess after this?
You mean like how RowHammer happens? Yes. Yeah, so we have in the literature different circuit level models or physical models that explain how RowHammer happens. Basically, what happens is you have different error mechanisms over there based on the charge leakage, charge trap. So when you hammer one word line, basically, it can create some electric field around it, and then it can drift some electrons, and those electrons get stuck at some points that exacerbate the leakage. Or when you hammer word line, you keep changing the voltage, and there is a parasitic cross-coupling across different word lines because those are basically metal layers in parallel to each other, right? And when you activate pure charge, apply high voltage, low voltage, you actually can cause the parallel word line to have some little increase in the voltage or reduction. And then it can partially open up or turn on some access transistors in the nearby row. And that way, it again exacerbates the charge leakage. And as a result of that, basically, you lose your charge in your DRAM cell, in your victim DRAM cell, and yeah, you have this effect. So this paper is not looking at the like root cause of why this bit flips happen, but it's more about okay, so we know this error characteristics, error mechanisms characteristics, but how do they change on real chips when we put them under different conditions, right? So I don't know. Does that answer your question?
So it's more due to the coupling of the word lines, not coupling of capacity.
So there's certainly that effect as well, and these results are not enough to explain like which one is more dominant than the other one. Yeah, I think yeah, we need more analyses on those in the circuit level. Unfortunately, it's not very easy to perform with the infrastructures we have access to today. Yeah. It's hard to say that it's the main reason or not.
Any other question? Yeah.
Could you use microphone? No, maybe you can use the other microphones like around you. Sometimes some of them don't work.
Actually, it's
Okay.
okay. So you show that HC first of most row is higher than the normal, right? Like 90% is 2x has the 2x HC first.
Yes.
Like, can we use some, let's say, already implemented error mitigation mechanisms to mitigate those 10% of rows? For example, can we use ECC to mitigate those errors on those lower HC first rows?
So we propose ECC for more vulnerable columns in particular in the search. And the reason is that when you look at a row, you actually have like 8 kilobytes of data, right? And prior work actually shows that RowHammer vulnerability has dependency on the data pattern. So when you put different data patterns, or let's say this way, by putting different data patterns in your aggressor row and victim row, you can force bit flips to occur in like precisely in particular locations. So that actually is the thing that defeats ECC. So when we look at like this kind of 8 kilobytes of data, for example, protecting the whole 8 kilobytes using ECC is hard, in my opinion. But when you look at like, if you look at this kind of distribution, for example, like, okay, this column is obviously more vulnerable than the others, right? So it's just like 1 bit. And you can replicate this bit 3 times, for example. Or you can just retire this column, right? Or you can craft an ECC that actually assumes that there's a higher probability of bit flip occurring in this particular column. Yeah, things like that. But in the whole row granularity, I think it's a bit hard. I'm not sure if it's even possible. Do you have ideas?
Maybe we can lower this 10% to, I don't know, 5 by that already implemented, but yeah. What you said makes sense.
Okay. Yeah. So in my mind, this kind of variation should be addressed or leveraged by basically configuring your already existing RowHammer defense mechanism for like different aggressiveness levels for different rows. Or maybe you have a mitigation mechanism already taking care of all rows, and there's an additional more robust, more proactive, more aggressive RowHammer defense that only takes care of these like small number of rows. So if you have small number of rows with high vulnerability, you can make some special treatment to those. I'm still not sure about ECC though.
Any other question?
Do we have anything on Zoom or YouTube?
No, there is no question there.
Okay.
So then I think we can wrap up today's meeting.
And wrap up the semester, I assume.
Yes.
And Merry Christmas, everyone.
Yeah, Merry Christmas, everyone.
Happy New
and
Year.
We wish you a very nice holiday season. And hopefully we will be in touch soon. Thanks a lot.
Thanks.
Thanks a lot for bringing the students.
Should I just leave the meeting?